Hello everyone, welcome to this lesson. So in this lesson we're going to go through the Python code for the Newton-Raphson method. Now if you remember, the Newton-Raphson is the first method, part of the open methods, which use one guess to find a root of an equation. And we have gone through in the previous lesson 3 different applications of the Newton-Raphson, and we have shown that for the first guess and for the 2 subsequent estimations, we basically got the derivative at that particular point, and where that derivative or that tangent intercepted the x-axis, this is going to be our estimation of the root. And we have found out that this is basically, we derived the Newton-Raphson by the equation of that particular slope, which is the rise of f of xi divided by the run, which is xi minus xr, and we have seen here, and we have rewritten this equation in terms of xr, and now we have this expression for the Newton-Raphson, which is xr is equal to xi minus the function at xi divided by the derivative at xi. When we examined the first guess as 1, we got a xr of 3, where the function at this point is -2 and the derivative is 1, and this gave us a true error of 50%. We basically took that approximation now, which is 3. We took the function value of it, which is 4, and also the derivative, which is 5, gave us a better root of 2.2 with a true error of 10%. And we took that 2.2, basically took the function value at it, which is 0.64, and a derivative, which is 3.4, and that gave us an even better root approximation of 2.012, and with a true error of 0.588%. Now, the code for the Newton-Raphson is very, very simple. The first thing that I want you to see is now the xr is defined in terms of one guess, and the function value and the derivative. But when it comes to the false position, you can see that it was the upper lower limit and only the function. We were not dealing with the derivative. And also for the bisection, it was just merely the upper and lower limit. So for this case, when we're developing the Newton-Raphson code, we're basically going to be defining the function, which we have with the false position and the bisection here, x squared minus x minus 2, and also we're going to be defining the derivative as dy. Also, I'm going to be using a lambda expression, lambda x colon, and the derivative of this polynomial is 2x minus 1. And here, the initial guess, instead of the upper lower limit for the bisection and false position, we only have 1, which I'm going to call xi. So xi here, I'm going to start with 1. Here, this is the initializations are very, very similar. We have initializing the approximate error at 100, and also the I here is to count how many applications of the Newton-Raphson are we doing, and we're going to start with I equal 1. This is the header. I want to output the application, its corresponding approximate error, true error, and also the root for each iteration. Now here, if you look at this code as compared to the bisection and false position, you're going to find that now the xr is defined differently using this equation that we have derived here, which is basically xi minus f of xi, the function at xi, divided by dy xi, which is the derivative at xi. And here you can, relative to the false position, you can see here we had a line of code or a block of code that identifies the section where the root exists, and this is not going to be the case for the Newton-Raphson, so we have omitted this block of code, and we're going to be remaining with everything else that we have had in the previous code, which is the approximate true, storing the root for the next iteration, and also upping the I, which you can see here. Those are identical codes here. Here, we're going to be approximating the first root, which is 2. So I'm going to be defining the true error in terms of 2. So actually, let's run the code. So if I run the code, it took 5 different applications. You can see we have gone below 0.1%, and this is the first error we're going to be examining at 0.002. And you can see even the true error is 0. So we actually reached the root of 2 in 5 different applications. I'm not gonna go to 0.01 because we're already below 0.01. So let's actually go to 0.001, which is probably going to go to 6. So to 6 different applications. Now we're at 0 approximate error, 0 true error, and we're at the exact answer of 2. So let's actually find the next one, which is basically -1. And the thing that I want you to see is actually your root or the guess will determine how many applications you're going to converge. So if I take maybe, for instance, a guess that is closer to it as 1.5, so let's examine how many applications it's going to take to reach there. So you can see it took 4 different applications to reach the root as opposed to 5 because, 1.5 is closer to 2 as 1 compared to 2. If I, for instance, take a initial guess as 3, let's see how many applications it's going to take. It's going to take 5 to reach there with 0 approximate error, 0 true error, and 2. Let's actually take a guess that is closer here, like -1.5, for it to find the root on this side. So you can see that this, or all of them, the bisection, false position, and Newton-Raphson, can find one root at a time depending on the guesses. So let's start 1.5 as our guess. So you can find if I used, oh, that's negative, my bad. So let's actually run this. Okay, as you can see, 4 different applications. It took four different applications to reach the -1. And here we have an approximate error of 0.000052. Let me change the true error here to give us the correct values for the true error for each iteration. So you can see here, and you can play around with different approximation to see how many applications it's going to take to converge. Let's see -0.5. If I do that, still 4 different applications, and it converged to our root, -1. So you can see from this lesson, it's actually a very, very simple code. The difference between the Newton-Raphson and the false position bisection is, one, you need to know the derivative of the function that you're actually dealing with. And you can see that we have actually omitted the code that identifies the section where the root exists. So we omitted this code and we added the derivative, and now since this is an open method, we're only dealing with one initial guess. And we're also presented that depending on how good your initial guess is will depend on also how many applications it's going to take for you to converge to your root. But in this case, we have found it was around 4 or 5 applications for us to converge to a root of 2 and a root of -1. Now in the next lesson, we're going to be introducing the secant method, and also in the lesson after that the Python code. And you're going to find sometimes you don't know the derivative, so we're going to be developing a method to create an approximation of the derivative, and this is going to be called the secant method. So that's it for this lesson, and I will see you in the next lesson. Thank you very much.